We're going to switch gears and we're going to talk a little bit about graphs and how they relate to kinetics. Okay, so first, let's say we have a problem on a test that gives us this graph and it says, what is the order of this reaction with respect to A? Where's the first place I'm going to look on this graph? Y-axis. Y-axis is natural log of A. What order is this reaction with respect to A? First order. Okay. Now, I also have over here an equation. It says Y equals negative 0.157x minus 2194. So what is the rate constant? So we've got four options there. It's somehow related to those two numbers, those options. If you think it is A, you're going to show me one finger. If you think it's D, you're going to show me four fingers. Yeah, just going to look at the slope and make it positive. 0.157 is our rate constant there. Okay, we have looked at energy reaction diagrams. Remember, our vertical axis here is energy. So this is a different kind of graph than what we had before where we were looking at concentration. We're looking at how much energy it takes to do things. The reaction progress, we can kind of think of as being like time. It's not metered. It doesn't have a certain number of seconds, but we start with our reactants, we end up with our products, and we have a hill. Now, Monday, we're going to get to the place where we have multiple hills along the way. But for today, we're just going to look at our regular diagrams. Okay, so they show the energy changes in the chemicals as the reaction progresses. So we can look up in our tables of chemicals and thermodynamics this reactant NOCl and figure out what is the energy of that particular reactant. And then we can look up the energies of NO and Cl of our products and figure out what the energies of those are. But we have this hill in between. And so far we haven't really talked a lot about the hill, just said that there is a hill there. Now it's going to become important. But we always want to look at our axes. Okay? Y is the energy, X is the progress. We're going to be paying attention to the activation energy. So the activation energy is going from our reactant, always from the reactant, never from the, well, always from the reactant, we'll just say that, to the top of the hill. So this is how high I have to jump to get over that hill. It's not good enough just to get high enough to get to the products. I have to have enough energy to get over the hill in order to get to those products. All right, the other thing we can find from this is what we've talked about before, delta H, or sometimes you'll see it as delta G, depending on how they're measuring energy. That's just the difference between the reactants and the products, okay, from here to here. And again, if we found this in a table and this in a table, we could just subtract that. We don't need a graph to do that. But the difference between the reactants and the products is delta H. If delta H is positive, like it is here, because it's an uphill graph, is that endothermic or exothermic? Is endothermic. Okay, now at the top of the hill, we have what is called the transition state. So the transition state is where we have our molecules colliding and they're transitioning between being, they're transitioning between being the reactants and the products. So we have dashed lines on that molecule because we're starting to break bonds. It's not quite broken yet. They're still kind of attached, and we're starting to form bonds. Okay, so the old bonds are weakening, the new bonds are starting to form, and we've got an unstable molecule. Oops, went too fast there. Okay, key thing to remember here is that transition states are unstable and they only exist for fractions of a second, usually such a short amount of time, we can't even see them. So we just theoretically think about, okay, this has to be happening at some point. And there are some tests we can do to determine if we're right. but they are super fast. They're not around long at all. Okay, so this is just kind of showing the progression. We start off with this molecule over here where we have a bromine attached, and we've got this nitrogen monoxide coming in. They're completely separate. At the transition stage, the bromine is starting to break, and the oxygen is starting to form its bond. So that's the top of the hill. And then at the bottom of the hill, we've got the bromine is separate, and the oxygen is firmly attached. Okay, and then you can see on the graph, we have at the bottom labeled delta H of the reaction. So is this an endothermic or exothermic reaction? Exothermic, it's a downhill reaction overall. And then we also have EA marked. EA is the activation energy. Okay. Now we also have this other one marked, EA reverse. So there are equilibrium reactions, which we'll get into in the next chapter, which theoretically, if these molecules are banging into one another, why can't it go in the other direction? And sometimes it does, okay? So the activation energy to do the reverse process, to attach the bromine and get rid of the OH, that is a little bit higher of a barrier, okay? So it doesn't happen quite as readily. All right, so on this graph, what is the value, shout out the number of delta H? Or whisper it, that works too. Yeah, 72. B here is our delta H. What is the number of our activation energy? No, it's not the 72. 78, that's our activation energy. Which letter corresponds to the transition state? D is where our transition state is found. So often we'll put like a star symbol there, or you'll see like a fancy cross on some graphs there to illustrate that. All right, so here are some different diagrams showing different endothermic versus exothermic and showing different reaction transition states. So which one of these has the smallest activation energy? Labeled A, B, and C. Which one do you think? C. All right. If you were going to make a guess as to which one of these reactions would proceed the quickest, which would you think it would be? C. Yeah. The lower the activation energy, the quicker this reaction is going to go. So we can compare the rates, and the rates are related to the rate constants by looking at how high that activation energy is. So if I know how high the activation energy is, I know, is this a slow reaction or a fast reaction? Okay. So activation energy, remember, is having enough energy for the molecules to break those bonds and form new bonds. If I don't break the old bonds, I can't have a reaction. Okay, so that's where that activation energy comes in. We talked about that before. All right, we've also said that it's important for the molecules to be facing the right way. So if I go back to these pictures, it's showing how they have to be facing. If these molecules aren't facing in this direction, if they're coming end on instead of side to side, they're not going to react, okay? So that means they're going to have to hit each other a lot of times in order to get into the right position, okay? So this is showing all the different ways they could collide with one another, but only the bottom way is effective. So that's our frequency factor. They have to collide with the proper orientation. If they're not colliding at their active sites, basically the places where the bond is going to form, there's not going to be a reaction. Okay, so we can put all of that together, as chemists like to do, into an equation. Okay, so this is the Arrhenius equation. This is going to be our last slide. The Arrhenius equation looks like this. K times A. A is telling us about how much they are colliding with one another. And then E is our normal E. EA is our activation energy, and R is our gas constant, but it is the energy of the gas constant that we used in chapter 6. It's not the 0.0821, it's 8.314. And then anytime we have a capital T, we should be thinking temperature must be in Kelvin. So on Monday, we'll look at how we can do some calculations. All right. Don't forget to do your homework on active. Any questions? Try to stay dry this weekend. Don't get blown away. Don't drive through water. Can be deeper than it actually looks. Moving water can wash your car away. Even if it's shallow. Be safe.